This follows on from the talk I gave 2 years ago in Flawney, and it really is concerned with looking at Williams' solution for a notch and thinking about it in different ways which enable us to bring out extra elements of the solution. And I hope you're familiar with it, because I've got to assume that my audience knows something about this already. So the Williams solution looks at what happens at the state of stress near a notch in an infinite solid. So there's no length dimension in the solution. And the classical way of thinking of it is that there are two singular terms. There's a mode 1 solution, which corresponds to opening of the notch, just like mode 1 opening of a crack, and a shear solution, the mode 2. And whereas for the special case of a crack, these two terms are equally singular, they're both square root singular. If this angle here is less than square root, then the K1 term is more strongly singular than the mode 2 term. Now, the natural way to set the problem up is probably like it's written down here, and I hope you can, that's big enough to read. And the two things which collocate, which match this solution to a finite problem, are indeed the stress intensity factors K1 and K2. And that's fine. But we can look at it in a different way. You see, we know that this term is more strongly singular than this term. So that we know that if we get very close to the corner of the problem, the notch root, that this term is going to be more dominant than this mode 2 term. And yet that's not at all obvious what we actually mean by that, because after all, in this problem there is no length scale, or at least no physical length scale. Now, the clue, in my opinion, to the way that we look at this is we know that these stress intensity factors do not have the same dimensions. They're different. So we can bring out the length scale by defining this thing here. I hope that's big enough to read. So it's the ratio of K2 over K1 raised to some function of lambda. And the lambdas, don't forget, we know those from the Williams solution. So this d naught has got dimensions of length. So what I'm suggesting that we do is, when we consider this solution here, that we actually consider, instead of K1 and K2 as being the parameters which scale the solution, we consider it to be two other things. D naught, which is this function of K2 and K1, and G naught, which is this function here. And these exponents, I don't know if they're big enough to read, but they're just given functions of lambda. So they're known numbers. So this means then that if we know K1 and K2, we can find G naught and D naught. And we can rewrite this equation here in this form. So that the stresses are proportional to G naught, and this is just seen as some kind of multiplier of on the loading of the problem, the magnitude of the loading. And D naught, which is now an internal parameter within the solution. So now D naught is actually something to do with this boundary between mode 1 and mode 2 loading. Okay. Now, I hope that I've managed to convey something of this and you're considering what's going on, because what we now want to do is to consider, as it were, some further internal properties of this semi-infinite solution, so that when we apply them to a finite problem, we can say more about it. Now, what I'm really thinking of is this. I did a PhD exam a while ago for Bjorn Skallerud in Trondheim, and the candidate had done a lot of very clever experiments, and she'd assumed that you could assume a mode 1 stress field at the corner of this problem. And it wasn't justified, and it made me think about whether or not it was possible to do a justification. Right, now what I've got here are a set of plots of simply von Mises yield contours. I expect you're very familiar with these. Let me just explain a little bit more about this. So there are three plots here on different scales, and these are obviously physical dimensions, but they're for the semi-infinite problem, so that the x and y normalize with respect to that thing d naught, which I'm at the moment carrying as a parameter. And I'm sorry the numbers here are too small to read, but this number here is 10 to the minus 4, that's 10 to the minus 2, and that's 10 to the naught. So this is 100 times bigger than this, and this is 100 times bigger than this. And the colour scale is, of course, the magnitude of the loading. It's G naught, this multiplier on the solution that you can calculate straight away from K1 and K2, normalised with respect to little k, where little k is the yield stress in pure shear. So what we're talking about is looking at the way the the notch root process, plastic zone, changes character as the magnitude of the applied load is increased. So I'm afraid also this is not very forgiving in the sense that each of these diagrams has a separate blue to red scale, but actually G naught over K is going from a very, very small value here, gradually getting bigger through here, and bigger and bigger and bigger still here. Now, what this is all about is as follows. If you had a problem in which you had only the mode 1 load, or the mode 1 solution excited, then of course at every scale you just get a mode 1 stress field. But if you have a mode 1 and a mode 2 present in the external field, then you'll get something where you're going to get this combined result at the notch root. But because of what I was trying to explain on the last slide, that if we were in here, it would look like a mode 1 field, and as we get bigger, it looks more and more, and eventually it would look like a mode 2 field. So we can see this evolve in this diagram here. Now, I emphasize again that so far in this I've done nothing other than look at the Williams solution itself. So the way that I would expect you to use this in a problem is that you would calculate the mode 1 and mode 2 stress intensities from the finite problem. From that you'd calculate my two new variables, D naught and G naught. G naught would then give you the magnitude of the loading here, and then you could see that if the loading was sufficiently small that it looked like the vertical figure of 8 that we're all familiar with, you've actually got mode 1 loading in the region that really matters, where cracks or whatever is going to start at this corner, whereas if you got the loading sufficiently high that it's turning around like this, then the crack is going to start in a combined mode loading. And the beauty of this is that you can say it all within the Williams solution. Okay, so that's where I got to 2 years ago. So you should think I should have the problem solved by now. Well, in fact, what we're moving on to is actually trying to use the same ideas to think about applying them to potentially fretting problems involving contacts. So here's a sketch, or set of sketches, of some so-called complete or sharp-edged contacts. So there's a shrink fit problem here in plain form as a cantilever beam, square edge block on a table, shrink fit here in axisymmetric form, or these spline teeth here. And we now realise that in these problems there are potentially two slip problems occurring near the edge of the contact. There's plastic slip if the state of stress is high enough and the corner sticks, and then potentially there's also frictional slip because the interfacial contact pressure might not be high enough, and you'll get a very small amount of region of slip causing fretting damage, and that can cause fracture, as you can see in this example here. So what I'm really trying to do in this sort of sequel to Forney is to say again, can we actually learn anything about the conditions at one of these contact corners from Williams' solution alone, just from that alone? And in particular, can we answer this question, namely, is there any slip present at all? And secondly, if there is slip present, is it so small that the plastic zone envelops it, and therefore we can consider the thing more or less like a monolithic notch? Or is the slip zone bigger than the plastic zone, so that the fretting damage really is likely to be important? And you can see this as a practically important question, because some problems that we think of as fretting damage are actually probably more like notch corner problems. So all that we're going to need to do to start off with is to take our Williams solution, and we conventionally draw the sketch like this because we think of this as the mode 1 and this is the mode 2, and we rotate it so that this fits in the corner of the specimen, and we assume for now that the coefficient of friction is high enough to eliminate all slip, so that this is the interface, but effectively we can consider this component and this component as a monolithic entity, as a single body. So I've drawn it here with a punch with a general angle phi, but in the last sketch I made phi pi by 2, and in the rest of the slides for this talk we assume always that this is pi by 2. Right, so suppose that we've carried out the Williams solution, and we know the eigen solution. We know everything about the state of stress in this neighbourhood. Now, for a notch, we naturally refer the solution to the bisector, because that's where the mode 1 solution and the mode 2 uncouple. But for the contact problem, what we're really interested in is this interface here. So we can write down the contact pressure in terms of the mode 1 solution and the mode 2 solution, and the shear traction, which is what the letter Q is for. It's similar to this, but it includes these numbers here, which I've given the letter G to, which are just elements of the eigenvector. Now notice that for 270 degrees, lambda 1 here is 0.544, so the lead term is just less than square root singular, whereas the mode 2 solution, lambda 2 here, should be 2, is 0.91, so that this is only just power order singular. It's x to the minus 0.1 or thereabouts. So that the mode 1 solution is much more strongly singular than the mode 2 solution. So now let's think about this problem of pressing a block down on another large plate with a force B, and possibly shearing it as well with a shear force here Q. And suppose that we're interested in these corners, of course, and that we get closer and closer and closer to this corner here. So that as we do that, we'd expect, assuming it is sticking, the Williams solution to be satisfied, to quantify what's going on. And so the ratio of the shear traction to the contact pressure is just the ratio of these two terms that I showed in the last slide. But you'll remember that the mode 1 solution is nearly square root singular, whereas the mode 2 solution is much more weakly singular. It's only x to the minus 0.1. So that if we make the observation point closer and closer and closer to the corner, we can neglect these two terms by comparison with these two terms, and then you can see that even the stress intensity factor cancels out, and the only thing we're left with is this one number from the eigenvector for the mode 1 solution. And it turns out for 90 degrees that number is 0.54. So what that tells you is that if the coefficient of friction is at least that value, this corner will stick. Now notice that solution is totally independent of the geometry of the problem, other than that these corners are 90-degree corners. So that tells you then that if you have a square-edged contact, and I do mean square-edged, that these corners will stick when you push down and indeed when you shear it, providing the coefficient of friction is at least that value. Just out of interest, if it's a 120-degree punch, that number's 0.3, so if the friction's at least 0.3, the corners will stick there. Now, I can see you don't believe it. So we did some FE with this as a monolith, right? So no contact elements, just bolted together, a single entity. And on this graph here, we've got what happens along the interface. On this axis is the ratio Q divided by P. So notice that the contact pressure and the shear tractions individually go to infinity at the corners, but the ratio between them remains finite. 0 is here. So the top line is what happens, this line here is what happens when you just push down. And as you can see, it's antisymmetric. And it goes through the magic values 0.54 at each end. So it verifies that the Williams solution is true. If you start to put a shear on, then of course it becomes more complicated, it loses its antisymmetry, and we start to come down here. And eventually, of course, it turns out that the ratio of the shear tractions is bigger in the middle than at the corners, which is what you'd expect. But the corners remain fixed, pinned at those values. So what that tells you is then that even if you had say you had a coefficient of friction of 0.7 somewhere here, that eventually as you pushed harder and harder, an interior point would start to slip. And then that slip would get bigger and bigger and bigger, and the last points to slip would be the corners. Okay. So let me just stop there for a minute. So where we've got to then is to say that the Williams solution can tell us when a contact corner is emphatically turned into a notch, simply in terms of the friction needed to stick the corners together. Now what I want to do is to try and take this calculation a little bit further and to say that even if this condition is not satisfied, say the coefficient of friction here was 0.5, how big would the slip zones be? How big would the plastic zones be? Would the plastic zone envelop the slip, or would the slip envelop the plastic zone? All based, I hasten to say, of course, on an elasticity solution. So we're just looking at violations. There's no flow rule or anything like that in any case. So this is the drawing that you've already seen. And what I'm now going to make a further approximation here. Instead of looking at the whole of the plastic zone, I'm just going to look at the value that it takes along the interface. So X with a subscript P is the magnitude of the plastic zone along the interface here. So you put von Mises' yield parameter together, and you set it equal to the yield condition, and then this is the result for a 90-degree punch again, a 270-degree solid. This is the magnitude of the applied load in terms of this G0 quantity, and this is the size here of the plastic zone. Now, I want to make this point next. When you do notch calculations, you can afford to be very careless about the sign of the stress intensity, because the plastic zone is positive definite. It only depends on the square of the stress intensity factors. So whether you're crushing a notch closed in mode 1 or pulling it in mode 1, you get the same implied solution. Of course, you've got to be much more careful than that when you've got a contact present, because the contact will separate. It cannot support any tension. So what I've just done here is I've just sketched out for this particular problem what the stress intensities turn out to be. So here's a block on a table again, where we're potentially pushing it down, we're shearing it, and we're also pulling the half plane that's underneath it. So all three of these modes of loading, the P0, the Q0 and the sigma 0, all three excite both stress intensities, both excite both the mode 1 loading and the mode 2 loading. But what I really wanted to draw your attention to is the signs. So that when we push down on this, at both of these corners, the mode 1 loading is negative, which is what you'd intuitively expect. You'd expect the corners to be sort of crushed together. If, on the other hand, you pull the rug from underneath it, this line here, then both of the corners tend to open up. And again, you intuitively probably expect that. When you shear it, this corner tends to be closed up, that's that number there, whereas this one is opened up, that's that number there. So all I really want you to get from this slide is that there are signs attached to these stress intensities, and we've got to be very, very careful about them. Now, when we're thinking about the possibility of slip at the solution, at the corner, don't forget that all of the stresses scale with the stress intensity factors, so that there's no, if you double all the loads, you double the contact pressure and you double the shear force, shear stress. So that we'd expect the solution to depend on on far fewer things, in particular the magnitude of the load, when we're thinking about the possibility of slip and separation. Okay, so here I've got an example, two example plots for two cases. Let's look at this one first here. So this is the case then when you have, say you're pushing it this way, and we're looking at this edge here, so that K1 is a negative number, and it turns out that K2 is positive. So the corner is closed, and although it doesn't look like it here because it's rising very steeply, this is this magic number 0.543 again here. So providing that the coefficient of friction is at least that value, then the thing will stick. If it's less than that, then you get a slip region, and this is the slip length. And there's a mistake on this that I realised 5 minutes ago. This only looks actually at the mode 1 loading. If it's lower than 0.2, there'll be an even bigger region of slip here. But let's put that to one side. Now, if you've got the same problem, we're dragging it along and we're looking at the trailing edge. Now, K1 is positive and K2 is positive. So what that turns out to imply is that the mode 1 solution implies local separation, whereas the mode 2 solution implies closure. And that's this graph here. So this again is distance from the corner, normalised with respect to this number. And this is the coefficient of friction. And you can see that in this case, for all practical kinds of values of coefficient of friction, you're going to get slip. You need an exceptionally high one to get any stick at all, and that's what it looks like. And at the corner, you've got separation. Right. So, these two plots are simply for the same thing. They're for these corners, but one of them, this one is with this sign of loading, and the top one is with this sign of loading. And they will give you, internally within the Williams solution, just as a function of the coefficient of friction, how big the slip and separation regions are. Whereas this graph here gives you the size of the plastic slip zone as a function of the applied load, and it is of course independent of the coefficient of friction. We're just assuming it's high enough. So it's sufficiently high to prevent all slip, all frictional slip. Right, so if we now compare this result with this result, we can find the boundary where the extent of frictional slip and plastic slip are the same. And that's what we get here. So this line here is where the friction slip and the plastic slip are the same length. So if you have an extremely high level of loading and an extremely high coefficient of friction, the plastic zone will envelop the slip region. For all other cases, the slip region, frictional slip, is bigger than plastic slip. Whereas at a corner that looks like this, you only need a relatively modest coefficient of friction before plastic slip dominates frictional slip. Okay. So for corners of this type, it's like a notch, and you can, for practical purposes, probably forget the presence of slip. And the reverse is true here. So here, fretting damage is likely to be a problem. Here, it's like a notch. So I'll just conclude by applying it to one problem. So you can see how the normalisation works out. So you've got this block problem again. And let's just consider one kind of loading. So let's just push down on it. So we're not going to drag it. We just push down. So P0 is the applied load. A is the size of or 2A is the size of the pad. And these are the calibrations for the stress intensity factors. So you know how to calculate the K1 and the K2 given the P0. From that, you can calculate the G0 in terms of P0. And again, if only I'd thought about this yesterday instead of today, those of you who are on the ball will realise that it would be ridiculous to put this value as high as 5. The thing would have gone completely plastic by then. A more sensible scale here would have been from about 0 to about 2. But anyway, if you calculate it, if you know a particular contact pressure, you can calculate the value of G0. And if you put that value of G0 on here, this scale, you can calculate the size of the plastic zone. Okay? So you're now using the calibrations that I've already found within Williams' solution, and you can say explicitly how big the plastic zone is going to be. If you then apply it to this diagram that I just showed you here, where we said you get sticking here, slip here, then you can see that for this value of G0 over K, if the friction's bigger than at least this value, about 0.4, we're up here where you get stick, whereas if it's the very low value down here, then you'll get slip, and fretting will be important. And that's it. So what I really wanted to get over today was that when we re-look at Williams' solution in the way that I proposed, you can get quite a lot out of it. You can fish out of it the internal length scale that you can carry as a parameter in the calculations. You can say whether or not the local plasticity is mode 1 or mode 2 in character, and that's a sort of, I want to emphasize that's a local feature of what happens within the neighborhood of the corner, and you can calculate that for different remote mode 1 and mode 2 loading. You can look at the coefficient of friction needed to make a sharp edge contact stick at the corners, and you can do that in a very simple closed form way. And you can find out when there is slip there, how big that slip zone is, and whether the slip zone is bigger than the plastic zone or vice versa. So you can decide whether or not fretting is likely to dominate crack initiation, or whether it's likely to be notch-like. That's it here.
Thank you.